In this video, I'll talk about half-life. In chemical kinetics, the half-life of a reaction is the amount of time it takes for the concentration of the reactant to drop to 50% of the initial value or the initial concentration. We'll talk about three types of reactions: zeroth order, first order, and second order. So first, zeroth order. The integrated rate law for the zeroth order reaction is this: the concentration of A at time t is equal to the initial concentration minus Kt. K is the rate constant, T is the time. So the question is, when will this A becomes 50% of the initial concentration of A? So we just plug in this A at time t to be 1/2 of A naught. So just plug it in, okay? And then that corresponds to the half-life. So I replaced this T with T sub half. This is the half-life. And then we just reorganize this equation and we get half-life equals A naught over 2K. It's that simple. For example, if K is 0.2 molar per second and we have the initial value of the concentration of A, let's say it's 1.0 molar, plug in these two numbers, 1.0 molar on top, 2 times 0.2 molar per second on the bottom, we get the half-life is 2.5 seconds. Also, we can look at this spreadsheet for this situation. K is 0.2 molar per second, 1.0 is the initial concentration of A. So we have this Excel spreadsheet, and then you can see where does this A drop to 50% of the initial value. Initially, it's 1 molar, so half-life, that means we're looking for the time at which A is 50% of 1.0. So somewhere here, and then you can see it's roughly 2.5 seconds by just looking at this Excel graph. So this is simple. What if we are dealing with first order reaction? The integrated law is a bit more complicated. It's the concentration of A at time t equals the initial concentration of A times an exponential function. And this is e to the power of negative kt. Again, k is the rate constant, t is the time. So what we need to do is, again, we just replace this A sub t with 50% of A naught. And then this t is t sub 1/2, the half-life. So we got something like this. Again, if you compare this equation and this equation, we simply replace this concentration of A at time t with the concentration of A at half-life. And what's the concentration of A at half-life? It's just half of the initial value of A. And then again, T should be replaced with half-life, T sub 1/2. And then we solve this equation. A naught and A naught cancel. On the left-hand side, you have 1/2. On the right-hand side, you have exponential function. You take the logarithm of both sides. And then you get negative ln2 equals negative k times half-life. And then we have half-life equals ln2 over k. So this is a little bit complicated. And then we just look at some numerical example. If k is 0.2 per second, the initial concentration of A is 1.0 molar, and then the half-life is ln2 over k. So it's ln2 over 0.2. It's going to be 3.466 seconds. And pay attention here, this equation does not involve the initial concentration of A at all. So it only depends on the rate constant K. Alright, so now let's look at how A changes with time for the first order reaction. So this is how A changes with time. And then if we look at this graph, we see the initial concentration is 1. So really we're looking for the half-life. That's when this A becomes 50% of the initial concentration. That's 0.5 molar. So right here. So if we look at this data point and then we check the corresponding time. Yes, indeed, it's roughly 3.5 seconds. All right, also you can just plug in the number here to get half-life. This y is 0.5 right here at half-life. So 0.5 equals 1 times this exponential function. Solve the function, you'll get y, or you will get the half-life x. All right, again, roughly 3.5 seconds, but more accurately, it's 3.466 by using ln2 divided by the rate constant k. Right? Now, second order. The integrated rate law for the second order reaction is the reciprocal of A at time t equals the reciprocal of the initial concentration of A plus kT. So again, to get the half-life, we just replace this A with 1/2 of the initial concentration of A. So this should be 1/2 of A naught. And then we replace this T with T sub 1/2, which is the half-life. So that's why we got this equation. And then by looking at this equation, we realize that this part is actually 2 over A naught. And then 2 over A naught minus 1 over A naught, we'll be able to simplify this equation. We'll get the half-life equals 1 over K times A naught. This is the final expression. And then we can plug in some numbers. If K is 0.2 molar to the power of -1, second to the power of -1, and if the initial concentration of A is 1.0, the half-life is 1 over 0.2 times 1, that's 5 seconds. Again, pay attention to the units. It's very important. Look at the unit of this K. It's m to the power of -1, s to the power of -1. And then the unit of this A naught is molar. So if you multiply these two together, you get second to the power of -1. And then it's on the bottom. So 1 over this K A naught is in second. So that's good. Always pay attention to the units. Again, the half-life for this second order reaction is 1 over K times the initial concentration of A. In this case, the half-life does depend on the initial concentration. Again, for the 0th and second order chemical reactions, the half-life does depend on the initial concentration of A. However, for the first order chemical reaction, the half-life is simply ln2, the logarithm of 2 over K, which does not depend on the initial concentration of A naught. Now let's look at the Excel graph. How does the concentration of A changes with time in a second order chemical reaction? The y-axis is actually 1 over A. The reason I say 1m over A is to get rid of the unit, because A is in molar, and if I say 1 molar over the concentration of A in molar, we'll just get a number without any unit here. And this is one way to label the axis. Another way you can say it's the axis is just 1 over A naught with a unit. The unit is molar to the power of -1. And then, again, this one is proportional to time. You can see this is really linear. This is because if you look at this integrated rate law, I want to show you this rate law again. So this is your vertical axis. What's the what's the horizontal axis? It's t. Now we have a slope. The slope is just k. What's the intercept? The intercept is 1 over A naught. So again, look at this. We have this equation. It's a linear equation. The slope is 0.2. That happens to be our k, rate constant. And this one is the reciprocal of the initial concentration. All right, so now let's think about the half-life. The half-life is when this y, or when this concentration of A becomes just 1/2 of the initial concentration. It's going to be just, 0.5 molar. But now this is the so-called reciprocal plot. So when this A becomes 1/2 molar, 1 molar over 1/2 molar is 2. So we need to look for, well, this is 2, roughly 2. Between 1 and 3, it's 2. So we're going to find the time here corresponding to 5 seconds. And indeed, our calculation tells us it's 5 seconds. 1 over 0.2 times 1, it's 5 seconds. So this exercise tells us how to calculate the half-life for a second-order chemical reaction. And by looking at this numerical example and this Excel graph, I hope you can understand how to compute the half-life for the second-order chemical reaction. Now some practice problems. The first one, the rate constant K of a first-order reaction is 0.50 second to the power of -1. What's the half-life? The equation is ln2 over K. For exams, you will be given this equation, but it would be nice if you can derive this equation yourself. So again, it's just ln over K. ln2 over K. ln2 is roughly 0.7. I think it's 0.693, and then divided by 0.5, you will get the half-life. And then more interesting question is this: how long does it take for A to drop to 25% and 10%? So this question, you don't even have to do the calculation. It takes one half-life for A to drop to 50%. And from 50% to 25%, again, the concentration of A decreases by 50%. Okay, again, from 50% to 25%. What's the percentage of the decrease? What you want to do is you want to do this 25% to divided by 50%. Also, the result is 50%. So for the concentration of A to drop to 25%, you just need two half-lives. First half-life, it goes from 100% to 50%. The second half-life, it's going to go from 50% to 25%. The third half-life, it's going to be from 25% to 12.5%. And then the fourth half-life, it will go from 12.5% to 6.25%. Again, you keep having the concentration. So over here, the answer is simply 2 times the half-life. And 10% is going to be a little bit tricky. So let's look at the answer. First, the half-life. ln2 over K, we plug in numbers, we get 1.4 seconds. So it takes another 1.4 seconds to further halve this A. Therefore, it takes about 2.8 seconds to reduce A to 25% of its initial value. And then, well, if you wait another half-life, that means another 1.4 seconds, the concentration of A will become only 12.5% of its initial value. Again, 12.5 is just 1/2 of 25. All right, but now let's look at this, the last question here, 10% of its initial value. So it's now more difficult to use the half-life to estimate this. It's not going to be an integer multiple of half-life. So we'll get back to the integrated rate law. The concentration of A is equal to A naught times this exponential function. We're going to just plug in numbers. So when does this A become only 10% of this A naught? Well, just plug it in. Just plug in 10% of A naught here. And then A naught and A naught cancel. You have only 10% left on the left-hand side. On the right-hand side, it's e to the power negative kt. Solve this equation. Well, you can just take logarithm of both sides. On the left-hand side, you will have log 0.1, which is just negative log 10. Negative log 10, I think, is 2.303. And then on the right-hand side, you have 0.5t. You do the math, you get 4.6 seconds. Anyway, you can use your calculator or use Google or use Wolfram Alpha to solve this equation. Again, it's going to be 4.6 seconds. This is a bit longer than 3 times the half-life. 3 times the half-life is 4.2 seconds because it takes 4.2 seconds for the concentration of A to reach roughly 12.5% of the initial value. Now this is 10% of the initial value. So no wonder it takes a bit longer. It's 4.6 seconds versus 4.2 seconds. 4.2 seconds again is 3 times the half-life. Now one more practice problem. The half-life of A is 20 years. Okay, that's a long half-life. So that means after 20 years, the concentration of A will become just 50% of its initial value. After 40 years, the concentration of A will drop to 25% of the initial value. 60 years, 12.5%. 80 years, 6.25%. Again, each time you just halve the concentration of A. So what's the reaction rate constant? And how long does it take for this A to drop to 12.5% of its initial value? So two questions. The reaction rate constant. Again, we'll use this same equation. Half-life is ln2 over k. Therefore, k is ln2 over half-life. We just plug in the numbers. We find the reaction rate constant, 0.035 per year. All right, it's ln2. ln2 is roughly 0.7. So you just plug in the number, you get this reaction rate constant. And because it takes 20 years to reduce the concentration of A to 50%, another 20 years from 50% to 25%, a third 20 years to further halve the concentration of A, therefore it takes a total of 60 years. Also, what you can do is you can use this equation to solve the problem. You just need to plug in the value of K here, and then you solve for T, and then you'll get T is 60 years.